All right, so just a few more practice examples of assigning point groups. So let's try this molecule here, trans 1,2-dichloroethylene. So this is a planar molecule. There's a double bond between the carbons and two hydrogens and two chlorines in that orientation. So again, we're going to use the flow chart or some flow chart. Is it a special group? Is it linear? No, it's not linear, obviously, and it doesn't have very high symmetry or very low symmetry. You can see, there is some symmetry to this. There's two things here, two things here, two things here. We expect there to be rotations or mirror planes or something, right? So what do? We go up here. Is there a C2 perpendicular to the CN? So first part of that, implicit in that, is we have to figure out the principal rotation axis. Are there any C's? And there is. There's one right like this. You can imagine this chlorine would get spun over 180 degrees. This chlorine and vice versa, hydrogens would interchange as well. Questions asking us, are there any perpendicular C2s to that CN we just found, to that C2? So are there additional C2s perpendicular to this C2? So that'd be something like here or here, maybe like that. And the answer is no. Any of those that you do, right? If you imagine this one, that would take this hydrogen and put it out into space here, and that hydrogen out into space there, so that's not symmetry element. The answer is no. So we're up here into the C's, okay? Or possibly an S, but we know from what I told you in the previous video, S is only one that just has an S, an identity. We already have a C, so we're a C. Is there a mirror plane? Okay, here's one that people miss a lot, is that if you have a planar molecule, there always is a mirror plane. There's always at least one mirror plane, and that's in the plane of the molecule. And so, you have a piece of paper. In that piece of paper, there is a mirror plane. It's in it. It's a two-dimensional molecule, but in three-dimensional space, it has a mirror plane, and that's in that plane, okay? And so this is gonna be a sigma H. Why is this sigma H? It's horizontal to the C2, right? The C2 is like this, and your mirror plane's like that. So that's good. So that brings us to yes, okay? There is, and is it perpendicular to CN? Yes, we actually answered that because it was a sigma H. So we're done. At this point, it's CNH, and we know what N is 2. And so this is actually C2H. There is actually one other symmetry element here other than identity, and that's inversion. Imagine this is at top left, it goes to bottom right, right? And so XYZ does go to minus X minus Y minus Z. But we didn't have to identify an inversion center in order to figure out the point group. And if you look at this chart, there's no question asking about inversion center. Turns out for this chart, you just don't need to ever look at that. Okay. All right. So let's do this one here. So this is three-dimensional one. It's an osmium center and it has 3 chlorine ligands and 3 carbon monoxides. The chlorines are in green here. And you can see in red and gray are the carbon monoxides around the blue osmium atom. So we start again, special group. Most of the time it's not going to be a special group. It's not super high symmetry. It's not like purely octahedral because there's different ligands. And so we're going to be up here. Is there C2 perpendicular to a CN? So first we have to figure out what the CN is. Well, there's a C2 and you can see it right here. You spin this 180 degrees, this goes to there, carbon monoxide goes to carbon monoxide. That's a C2. Is there a perpendicular one? You can look at this for a while and the answer turns out to be no. All there is left that you can find other than identity is these 2 sigma V's, mirror plane, vertical mirror plane. Why they're vertical? Because they contain the C2s and they go through the atoms, right? They're not D's because they're not bisecting atoms. And so yes, and yes, there are mirror planes, but there's no mirror planes perpendicular to the C2. So that got us to no. So that got us to CMV. Okay, and so N was 2, so C2V. Last one, I brought this up as an example, right? Earlier, bromochlorofluoromethane. 4 different substituents around a tetrahedral center, that has no symmetry, okay, other than identity. And so that is what we call C1. And it turns out this is chiral. And so in the next video, we'll go over some properties, including chirality, that you can get straight out from the point group.